Hello everybody, welcome back to the lectures on polymer science and processing. In this week's lecture we will discuss the properties of bulk polymeric materials and especially for elastomers and semi-crystalline materials. So just as a recap from last week, we started to discuss material properties of polymers. We discussed I introduced how we can actually measure and characterize such properties. Now we learned that we can use X-ray analysis to investigate the inner structure of a polymer material and then distinguish whether it's semi-crystalline or amorphous. And we can also look at the thermal behavior via DSC, differential scaling calorimetry. And this gives us the same information in a different setting. So there we probe phase transitions by measuring the energy that is supplied by a polymer sample with respect to a normal reference sample. And then we discussed for the amorphous polymers, especially the class transition temperature, which is a phase transition of second order, and it relates to a change in the dynamics of the polymers. So the crystal structure, or the, if you want, physical configuration does not change, but what changes is how efficiently these polymer chains can move. And that then determines if something is very soft and elastic or whether something is very hard and rigid. Okay, so today we want to move a little bit further and then discuss the consequences in terms of elastomers and then why can also be important to have crystalline domains within a polymeric material. Okay, so this is what's on the agenda today. So we look at thermodynamics, especially both of polymers, of elastomers and of semi-crystalline materials, and then we will try to see how this translates into macroscopic properties. Just as a recap, this is what we already discussed last week. Those are, if you want, the four different types of how polymers can arrange in a bulk, and we tick this off, and now we want to see what happens to an amorphous polymer if we cross-link it. And this is typically known as an elastomer. So again, you see here we have amorphous polymers, so polymer coils, and every now and then we have cross-linking points. So to make an elastomer, we need an amorphous polymer. It cannot be semi-crystalline because, as you will see later, this will change the property. So the polymers need to be in this coiled state, coiled disordered state, which is the key property of an amorphous polymer. And it needs to be cross-linked, but only very loosely, so that there is enough flexible segments in between cross-linking points. And this will resemble, well, for some of you, this will draw an analogy to polymer gels, where you see that a hydrogel actually works very similarly. You also need to have an amorphous and very loosely cross-linked gel. Here we don't have a solvent though, so this is just a bulk material. And so, as I said, we need to have these chains here in between cross-linking points. They need to be long and flexible, and they need to be able to move easily and to be dynamic. And that means the polymer needs to be above the class transition temperature. So amorphous polymers, so we have homogeneous chain movement possible. It needs to be above the class transition temperature to allow dynamics, and it needs to be mildly cross-linked. So what are the consequences of the cross-linking? For this, we need to do an experiment, or I will show you actually two experiments. One is we will see, or I will show you how the temperature changes if a polymer is stretched or then released. And the other one is we will look at the thermal expansion coefficient of a rubber, but for this we need to move into the lab. So let's look briefly at a very simple experiment, and this is something you can easily do at home. So now if you go to your kitchen and you look for, so let me go down a little bit, for a normal rubber. And then you take the rubber, you put it onto your lips, and then you pull very strongly. And then you let go again, and try again, and let go again. Okay, try to do this yourself, and then observe what happens. And if you do it correctly, what you will see is that while you expand, your lips will feel warmth, so the surrounding will heat up, and while it contracts, it will become colder. So something changes with the temperature of the rubber as we rapidly stretch and expand again. And this is something that we want to explain. Now for the second experiment, let's move over to the lab. and see how a rubber behaves when we heat it up. Wow. Okay, so now we moved over to the lab and we built this beautiful contraption here. And what we want to do now is show you what happens if we heat up this rubber while it's being stretched by this water bottle. So I'm switching on the heat gun and let's see what it is. We mark the initial condition here. And clearly you saw that it moved up a little bit. It's not a huge effect, but something very peculiar, that you have this negative thermal expansion coefficient. So what you've seen in this experiment is that as you heat up the rubber, the force becomes stronger, so the spring becomes stronger, and the material contracts. So this is a very peculiar behavior because it implies that the rubber, at least under tension, has a negative thermal expansion coefficient. And intuitively, from daily life, we know that materials have a positive thermal expansion coefficient. Now, if you heat something up, it will expand in volume. And why is that? Because you supply more energy, so the bonds start to vibrate more, the molecules can pack less densely, and everything expands. While for a rubber, it seems to be the other way around. It seems to contract when you heat it up. And those are now two puzzles that we want to solve by applying thermodynamics. Okay, firstly, what we want to understand is, why is a rubber actually elastic? So if I stretch it, why does it come back? Okay, and in order to do this, we first put up an intuitive picture, and that is the picture of a polymer coil. So you can intuitively, now we understood that because of entropy, because of the numbers of microstates, a polymer wants to coil up. And as we stretch it, we decrease the number of microstates. And this, of course, is not favorable in terms of entropy. So our intuition will tell us that the polymer will have a tendency to pull back as if we let go, not to increase the numbers of microstates. So what I mean by this is, hang on, let's go first here. So we have a state of high entropy, and as we stretch, we go to a state of low entropy. In order to do this, we need to apply work. This is why we need to stretch. And if we let go, it goes back into this configuration. And in order to do this, we want to dig a little bit deeper. And before we do this, let me briefly mention something that I just forget. So why is it important to cross-link a material? This you can see in this rheological data. This is G prime, so the elastic modulus. And you see if a material is not cross-linked, eventually the elastic modulus drops to 0, so the material cannot store elastic energy anymore and just starts to flow. And if you cross-link, you keep it at a certain level because the cross-linking points prevent the polymer chains from flowing. So they set anchor points that always induce a driving force back because the polymers cannot infinitely move away. Okay, so this is why cross-linking is important. But now back to this consideration. If the numbers of, or if entropy is important, or is the driving force of this rubber elasticity, then we should be able to answer this by considering the free energy without any contribution of enthalpy. Okay, and just to recap something that I alluded to in one of the earlier lectures, this is the distribution of chain ends in a freely jointed chain, so a Gauss chain, and this is the result of this random walk, three-dimensional random walk statistics. Remember, when we did this derivation, we covered this part here, so that gave us the average coil dimension, and with an accurate treatment, we get this omega of x, y, z, which is the probability of finding the polymer chain end somewhere in space, at a position x, y, and z, when the second end is in the origin. And that is given by this Gauss function here, okay? So the second thing to recapitulate, that the numbers of microstates in a chain is proportional to this value here. So the higher the probability of finding a chain somewhere, the more microstates must exist to bring it there. Now it's kind of the two facets of the same coin. Because if you have a high probability, you need to have a lot of possibilities of the polymer chain to be in that state. And that is the numbers of microstates. Okay, just to recap that briefly. And now we want to look into what happens to that function, if we want, or to the free energy if we stretch the polymer. Okay, and for this, let me move to the blackboard. So what we're going to do is we want to prove that indeed the polymer behaves as a spring and it is an entropic. So that the spring behavior is caused by entropy. And just to briefly mention that again, a spring is characterized by Hooke's law. That means if I pull on something, I have a restoring force that will bring it back. So Hooke's law is something that the force I need to apply depends on the extension x via this spring constant k. Okay, so now what we want to do is we want to see if we can replicate Hooke's law only considering entropy. So we know that a rubber must somewhat apply to or follow Hooke's law because it behaves like a spring, right? If you pull, then it will be drawn back. So in order to do this, we look at polymers, and we want to see how the free energy S as a function of R, and just for the sake of consistency, that we also call this R, so this is the position or the extension. G of R is H of R minus T S of R. And to see whether or not entropy is the driving force, we set this to 0. Okay? There's also a reasoning behind this. If I move the polymer chains back and forth, the enthalpy actually doesn't change. No, the chain itself does not change its energy because the state doesn't really change. It's still a polymer chain. What changes is the configurations of the polymer chains. And this is encoded in this S. Okay, so now that means that G of R is minus T S of R, and now we can apply Boltzmann's equation, and this is then minus K T ln omega. And again, omega is a function of R. So here is, if you remember from 3 weeks ago, this is S is K ln omega. And what I just said is that we can equate omega to this probability of finding a polymer chain somewhere. So that means using this random flight statistics, and let me just give you the formula again so that we have it on the blackboard. This is not something you need to memorize. I just want to show it to you that we see how this entropic spring arises. So we have omega, or omega of xyz is beta divided by pi to the power of 1/2 cube. So this is just a prefactor times exponent minus beta r squared. And this beta is 3/2 NL squared to the power of 1/2. And just again, to remind you, this is what we recovered when we did our very simple picture here. Okay? So now what we said is that we can equate omega with the likelihood of finding a chain at a certain position in space. And if we do this, then we get for delta G, or for G, as a function of R, we get minus kt ln W. And if we now put in this formula, then we get the logarithm of this one here. Okay, so this will be some constants, and I don't even bother to write down the constants because I'm not interested in quantifying this. I just want to see the functional behavior of this thing. So I get kt, which is this one here, times a lot of constants, and then times logarithm of the exponent minus beta r is minus, I already factored this in by leaving this minus out. Here's a square. Minus beta square r square. So, and this beta we can directly put in. So this would be beta square is 3 over 2 nl square, and nl square is r square, the average root mean square, or the average end-to-end position, and now times r square. And that's actually the only thing that counts. So there's an r square, a factor of r square here. Okay, this is from this one here. So now we have connected G as a function of the distance with this one here, with r square. So now we get an expression of the free energy as a function of the distance. And now we need to convert the energy to the force because we want to replicate Hooke's law. And the force is always the energy is the force times the path that you need to bring. So the force is the derivative of the free energy with respect to the path, or to r. This is dg of r over dr. So if we do this, then again we get a lot of constants. And this kt is also a constant, times constants. And this one is 3 over 2 over 2 r square. And r square, the derivation of r square is r times 2. So we can get rid of this one here. And now what we see is that this is simply a lot of constants, all of these, times r. Constants or material properties, now these r square, but this is not something that is a function of r. So what we get is F is k times r. And this is exactly what is predicted by Hooke's law. So we create Hooke's law. Only considering entropy. Note, because we've set h to 0 here. And that means that the spring behavior of an elastomer is caused by entropy. Okay, with this simple consideration, we can see this, not simply because we ignored h. Okay, so now, why is the rubber heating up when I stretch it? Now we see that first of all, like this, when I let go and it flies away, this is caused by the tendency of all the individual segments between the cross-linking points that become stretched out when I pull on them, that want to recover their normal coil configuration. This gives me the driving force to drive back the material. So now, as I stretch out, I create work. Now I use work onto the system. Since H is 0, and we can rationalize this, because, as we discussed before, there's nothing that changes in the bond structure of the polymer. So the internal energy or the enthalpy is not affected by the stretching. And the only thing that is affected is the entropy. So now as I stretch, the material cannot really store the energy elastically, and it just changes the entropy. And since entropy in a process cannot decrease, now this is the second law of thermodynamics, if I decrease the entropy of my system, then the entropy needs to go somewhere else. So all the work that I put in is converted into heat that is released to increase the entropy of the surrounding, which is kind of the vibrations and rotations of the molecules that I feel, or that increase, and I feel that on my lips because as heat. Okay, so this is the cause why the polymer heats up when it expands. If I let go, now the entropy of the system increases, and this increase in entropy requires energy, and this is taken from the heat of the surrounding. This is why it cools down. And why does it require energy? Because you can imagine the polymer coil doesn't entirely change by itself, but it changes by being hit by very small molecules all the time. And they nudge it more and more into a coiled state. And this is what happens as we let go. This is where the energy is taken out of the environment. Okay, so these considerations kind of clearly explain how the rubber heats up and cools down while stretching and expanding. So how about this negative thermal expansion coefficient? How can we rationalize this? Well, we already know that entropy plays a big role. Now this is what you see here. And now one could argue that entropy is of course always stronger the higher the temperature is. Now this comes from this Ts term here. So this would already tell us that with increasing temperature, we get a stronger force, a stronger spring constant. You even see this here. Now you have this temperature term here. This relates to K. If I increase temperature, K goes up. This means that the force bringing the spring together increases. Now you could also imagine that with increasing temperatures, you have more and more small molecules that poke on the polymer and kind of drive it into its compressed state. And the more energy these small molecules have, and heat is nothing else but the energy of the small molecules, the more efficiently the polymer can be compressed by these small molecules acting on it. And this then increases the volume of the polymer chain, and by this increases kind of the possibility of the rubber to compress. And that's related to this K here. So conceptually, it's actually very easy to explain, but I also want to show you that we can put this into thermodynamic equations as well to give you kind of a black and white answer. So in order to do this, we look at so the negative origin of the negative thermal expansion. In order to look at this, we go way back to, if we want, the origin of thermodynamics. The first law of thermodynamics is, I'm asking you, well, the energy of a system is composed of either heat or work. So du, the inner energy of a system, is composed of dq. System can take up heat, or you can provide work to the system minus dv, and this is okay. So this would be the pulling. Now the second law of thermodynamics states that entropy can never decrease, or in processes, entropy always increases. And for a reversible process, ds equals dq over T. So in a reversible process, we can equate the heat that is taken up by the system or released by the system with the entropy. In an irreversible process, this would be larger. But in any case, we can consider our rubber expansion reversible because, as you've seen, I can stretch it multiple times or hundreds of times, and it always comes back to its initial state. Okay, so now this is kind of like very fundamentals. And let's see what happens if we stretch a rubber band. And we say that we stretch it over a length L. And we use a force capital F. So now the work that we need to provide is minus let's call it K. KdL. That's what we had on the blackboard. That's Hooke's law. But K is the spring constant, and dL will be, I think, let me put it, F, to be consistent with my slides. And this small f used to be the K, the spring constant, in the other slide. Okay, so this is what we need to do. I'm pulling, and as I'm pulling, it requires work given by this equation. Now we can plug this all into this equation here. du is then TdS plus FdL. Those 2 times minus becomes plus. And then I can rearrange. FdL is du minus TdS. And now if I arrange even a little bit more, I can say F, which is the spring constant, so the resistance to stretching, is du over dl. And if you do this thoroughly, you state that this is at constant temperature minus T ds over dl, also at constant temperature. Okay, the temperature term is already here. So this now gives us a thermodynamic expression for the rubber expansion. This is the spring constant. Or the stress in the system. And these are the 2 terms from which it arises. So this apparently is a term that relates to the change in the inner energy upon stretching. And we already said this is actually small because there is not too much change in conformations. And this here is change in entropy. And we already said that this governs the process, but now we can see that ds over dl is the change in entropy as we stretch the rubber, is negative. Because the entropy decreases as we stretch out the chains. And if this is negative, then F becomes positive, or F increases with temperature. You see, this is a negative value, so this becomes positive, and that means F increases with temperature. That's something that we've seen in the other equations already before. So the spring becomes stiffer, or L decreases with constant F. So this is just a consequence of the other one. If I have the same spring and I pull with the same strength, and if the spring constant becomes stiffer, then the material contracts less. So the same force that I need gives me less deformation. Okay, and this is exactly, by the way, this should be with constant F. So the same force gives me less expansion, because I need more force to pull on it, and this gives me this negative thermal expansion coefficient, because the spring constant increases with temperature. So something really peculiar, only occurring in polymer rubbers, and here you see why that is. And now just to show you that this is indeed true. That's what you see here. What is plotted here is the stress of a rubber. So how much force I need to pull it to a certain length. And you see with increasing temperature, the stress goes up and up and up. Or if you come from very high temperature, the stress goes down simply because the spring constant decreases with temperature, caused by this term here. And suddenly there's a weird kink where it goes up here. And now my question to you is, what is this kink? Why does it by a certain temperature, why do you suddenly get a positive thermal expansion coefficient? Think about it. I clean the blackboard and then we'll discuss. So what's the answer here? Well, very clearly, from this point on, the rubber doesn't behave as a rubber anymore. No? And this is the glass transition temperature. Here the chains suddenly become very stiff and you cannot pull it anymore. And then, of course, it becomes stiffer and stiffer as you decrease the temperature because the thermal expansion coefficient is positive. But this is where, if you want the definition of a rubber, breaks down. Okay. And you also see that the contribution from energy, which in this diagram, of course, is the connection to the y-axis, is actually really very low, as we assumed. And from the slope, you can get this ds over di. Okay, which indeed is, as you see, negative. Okay, so what makes a rubber? Here is comparison of different materials. And you see that G prime is kind of the modulus of different materials, which is a good measure for the elasticity, similar to the glass transition temperature if you want, drops very rapidly for different type of materials at different temperatures. So you see for NR, natural rubber, it drops very early, minus 70 degrees or so. for certain types of polyurethanes, you come somewhat close to this. But you also see that PVC, polystyrene, PMMA, so materials that we all know or that intuitively are not rubbers for us, but hard materials, also have a similar change in properties at different temperatures. And this is just related to differences in the glass transition temperature. So you see, you can actually make a rubber of a lot of different materials. It just depends on the temperature of application. So you need to be above the glass transition temperature for a rubber to be a rubber. So if you work in a sauna, you could actually probably use polystyrene, if it's a very hot sauna, to make your rubbery materials. And that's also what you see here. So glass transition temperatures of selected rubbery materials. You see a polysiloxane, PDMS, again what we discussed last week, has a really, really low glass transition temperature, which comes from this high flexibility of the SiO bond. So these really make excellent rubbers also at cold temperatures. Then you see that polybutadiene, polyisoprene, this is natural rubber, also have application windows up to very low temperatures. That's something we discussed in the very first lecture, that, for example, airplane tires are often made of natural rubber because it has such an extremely low glass transition temperature. And here are synthetic rubbers, polyurethane or styrene butadiene block copolymers. This is the thermoplastic elastomer that we discussed a few weeks ago. And you see that they still behave as a rubber at room temperature, but their rubbery properties fail much earlier compared to natural rubber. Okay, so much for the rubbery state of materials. So we've seen that indeed entropy, well, this is another field of polymers where entropy is really the big player. And now I want to move to semi-crystalline polymers. So again, here you see our generic cartoon of semi-crystalline polymers. We have amorphous regions that are surrounded by semi-crystalline regions. And now I want to discuss with you some aspects of thermodynamics and especially what changes or why it is important, it can be important to have semi-crystalline materials. Okay, so first, let's see, why do polymers crystallize? For pretty much the entire lecture, I always showed you pictures of spaghetti and told you, look, this is how polymers behave. Now, it's very easy to put spaghetti into water and boil them and to make them look like this. And this is why I always said that, look, this is how polymers look like. However, in a semi-crystalline polymer, what we actually do is the reverse. We take the spaghetti and by some magic, it goes back into an ordered state. And that is very counterintuitive, and it's also directly opposing anything I've told you the entire time. So the question is, how can that happen? How do polymers crystallize? And in order to do this, well, and we will also want to see why it's important, what's the difference. So in order to do this, we just need to recapitulate a few things. In a polymer melt, we have the chains that are entangled and mixed. We have a very high entropy, we have a high free volume, and this is the spaghettis. And if we go to a crystal, we have the chains packed in a regular fashion, more or less, because it's semi-crystalline, so it really resembles this spaghetti. And this has a much lower entropy, and it also has a much lower free volume. How can this occur? And here, for pretty much the only time in this lecture, I'm changing my attitude, and now I say, and I can also leave it on the blackboard, it's not the entropy that counts, it's the enthalpy. So in the polymer crystal, the loss of entropy that we have must be overcompensated by gains in enthalpy. So here now we really play a different game to show us or to lead us to the crystalline state. Now we need to think about not what changes the entropy, we need to think about which factors we can use to increase the entropy of the system. And now I'm asking you, if you, from everything that we've learned so far, how can we increase the interactions between the polymer segments? Because nothing else is the enthalpy. So go back maybe in your mind through the lectures that we had before and think about what we learned, how polymer chains interact. Well, what we need to be looking for are attractive interactions between molecules. And matter of factly, there's quite a lot of quite different interactions, attractive interactions, that we can more or less all employ to make polymer crystals. So let me walk you through this. First, we can invoke van der Waals forces that work between all the particles. Now this is the most difficult one because they are generally fairly low, and if you want, the necessary requirement for this is that the polymer chains can actually pack in an ordered fashion. So very often, let's say for polystyrene or for materials that have a side group, it's impossible for them to pack in an ordered fashion because the side groups are not regularly spaced. Now, remember, if you look at this, so a polymer that looks like this, let me just draw a couple of units. If I draw, let's say, styrene, polystyrene, like this, I'm ignoring two things. First, I ignore that there's actually an H here, which is fine, because this is how you write structural formulas. But I'm also ignoring that there is two possibilities how these two bonds can stand. So either they can stand that the styrene ring points to the front, and the hydrogen points to the bottom, or to the back if you want. Or they can stand in a way that the hydrogen stands to the front, and the styrene ring goes into the back of the blackboard. And now, depending on whether or not this is defined or not, the polymer can or cannot crystallize. So if this is now random, random orientation, then we call such a polymer atactic. And atactic means that, well, as I said, there is no possibilities or no correlation between these positions, and that cannot crystallize. Simply because there's not a possibility to pack the chains efficiently because all of them look different. No, it's not defined how they stand. But there's also two other possibilities. I can have a polymer chain where all the substituents point in the same direction. So in this case, this would be called isotactic. And this can crystallize, you see, because all the rings stand in the same thing, so you can easily imagine how they can stack in an ordered fashion. And there was a third possibility, which I'm trying to squeeze in here. Where it's always alternating. So the ring stands to the front, now the ring stands to the back, now it stands to the front again, and so on and so forth. So there it alternates all the time, which is called syndiotactic. And it's the same thing. Here you also have the possibility to stack the material in an ordered fashion, because all of them can align and the benzene rings can stick, or doesn't need to be benzene, can also be a different rest. They can form a crystal. Okay, this, if you want, is kind of the zeroth requirement. And in the simplest case, polyethylene, you don't have these problems because it's the same hydrogen that is bound to the central carbon here, so they can really pack together. Okay, so order in the polymer chain can be induced by structural order if you want, or crystallinity can be induced by structural order. Well, a second possibility, and one that is much stronger and much more widely used for that, is hydrogen bonding. So this is something we discussed ways back in the lecture in the second chapter when we discussed step growth polymerization. You saw that in step growth polymerization, we have our functional groups in the main chain of the polymer. This is a polyamide, nylon, and these can undergo hydrogen bonding to neighboring chains. So you see, especially in polyamides, we have this possibility to do a hydrogen bond with two different neighboring chains, the upper one and the lower one, at each monomer unit. And that makes it very efficient to decrease the energy by forming a crystal, because you gain so much energy from these hydrogen bonds. And we already also discussed that this is more and more efficient the stiffer these chains are. Because with aliphatic chains, they always rotate and move, and you never have the right position between all of these hydrogen bonds. If you replace this by something stiff, like an aromatic unit, then you can align the polymer chains very efficiently, and it zips up like a zipper, and all the hydrogen bonds are in place, and you create an extremely strong and tough material. That's how you make bulletproof vests, for example. Well, there's one additional thing that I just want to show you briefly. This is known as pi-pi interactions. So this very frequently occurs between conducting polymers. So you see this is an example of a conducting polymer, a thiophene. And here you see you have an aromatic conjugated polymer throughout the backbone. That's what makes it conducting. It's not something we want to discuss in this lecture in detail, but you can see that there's electron percolation all along the main chain. And if you have extended pi orbitals, they can decrease the energy by so-called pi stacking. So all the aromatic units pack on top of each other to decrease the energy. And why that is, maybe we can just briefly show this to you on the blackboard, is because an aromatic system has orbitals that look like this. Now you have these pi orbitals that look like a sandwich where the C bonds are, here's the polymer, are aligned. So if now the next polymer comes, then these electron density can be somewhat delocalized via these two pi orbitals. And this increases the total energy, and this is why aromatic units tend to stack on top of each other. And that's exactly what you see here. So here's a crystal structure of such a material. Here this is how it looks like, and you really see these individual stripes of pi stacking. Okay, so very clearly an ordered structure. Good, okay, so this gives us, or these are examples of the incentives of polymers to actually crystallize. And now let's look at how such a crystal forms. So here we see very generally it has lamellar structure. This is what we already drawn multiple times on the blackboard. And there's different possibilities. So you could have a perfect lamella that always folds back and forth. And you can already kind of appreciate that this is very difficult to form because it requires a lot of precision for the crystallite. You can have something where you have smaller loops here. And you can have a structure where the polymers go in and out and fairly randomly form these lamella. And this is known as the random switchboard model, and that's kind of the most widely occurring type of polymers. But I'll walk you through these different possibilities. So just an example, polymers have fairly complicated unit cells because it's complicated molecules with a fairly low symmetry. As an example, polyethylene has an orthorhombic unit cell, so you see the chains kind of all align here in these lamella, and within the lamella they kind of pair like this. Okay? It's not really important. More important is that we have these lamella type structures. So I said it's very difficult to create something like scenario A, but indeed it's possible. And you can grow polymer single crystals, and it's not so easy, and you grow them from dilute solutions with a lot of precision. But if you are able to do this, then you get lamellar structures with adjacent re-entry. So you really have these sharp folds in the polymer structure. And this is how it looks like. And indeed, if you see something like this, they are polymer single crystals. That's maybe more a bit esoteric or just interesting to see that it works. Very typically in a bulk material, especially in semi-crystalline material, you have this switchboard model or lamellar crystals with a random re-entry of chains. So if you follow a chain, you see it can go from one lamella, stop here, or go to the next lamella. There is no incentive for each polymer to be only in one lamella. So everything is somewhat interconnected, which is also good because it increases the mechanical stability. So this is an example of a polymer, and you see here you have these individual crystalline domains. No, and in between you have amorphous regions, kind of here as well. Okay. So when you have a lot of these lamella in structures, very often you observe something that is called spherulites. And those are spherical superstructures consisting of multiple lamella. So they look kind of, if you start from the very beginning, you have these very small lamella, and they spread out radially, form these kind of bulky spherical structures. And if you look at them under polarization microscopy, you get these very distinct Maltese cross structures. So this is a telltale sign that you have polymer crystals in the form of spherulites. And how does such a spherulite look like? So here you see you have a nucleation site. Then you have polymer lamella that grow out radially. So they can sometimes kind of fold up and chain, and they are surrounded by amorphous material. And then you see that if this happens multiple times, then you create these spherical structures that kind of all touch each other. This is how a polymer crystal looks like in bulk. Okay, how can we characterize this? So we already mentioned this before. We can use X-ray analysis to actually see the crystals, and then we simply look at the area under the curves of the X-ray diffraction patterns, and we determine the amount of crystallinity, Xc, as the area of the crystalline materials, which would be here, 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 and so on, divided by the total area. So the amorphous area, which is the halo here, and the crystalline area. And this gives us then the behavior of, or the crystallinity of polymer shells. Okay, so just as an example, or kind of as an overview, how does it now look like? Now we need to factor in these two components. We have amorphous regions and we have crystalline regions in a semi-crystalline polymer. And we already know that below the glass transition temperature, our amorphous phase is in a glassy state. And the crystalline state is still in a crystal state. So this makes the material very rigid. And now, in difference to amorphous polymers, when the polymer starts to be in a rubber elastic state, so above the glass transition, T is larger than Tg but smaller than the melting point, then the crystalline units are still crystallites. And that means that they maintain the mechanical integrity of the material. And then this is often called a leather-like state, but in a sense it means that the polymer can be used as a material above the glass transition temperature. It will not flow away and it will not melt and disintegrate because of the crystalline regions. But then if you heat up further, then it goes into the melting region, and that is simply because the crystallites melt. Remember from last lecture, amorphous polymers do not melt. No, they become softer and softer and eventually maybe disentangle and become less viscous, but the melting is strictly speaking only a property that occurs with crystals. And at highest temperatures, of course, everything is then in a melt because the crystals have dissolved and the amorphous materials rapidly disentangle. Okay, so now what I want to discuss with you are the consequences for the material properties. And for this, maybe we make some space again. So we look at the properties of semi-crystalline materials. And now what we can appreciate is that a semi-crystalline polymer is, if you want, a composite of the amorphous regions and the crystalline regions. So let's first look at the properties of these two different regions. So we have amorphous regions and we have crystalline parts. So amorphous regions are not very densely packed. And as a consequence of this, because it's not so densely packed, they are rather ductile. So if you change or if you bend them, the polymer chains may be able to adapt. At least to a certain extent, of course. And this also gives them elastic properties. Now, if you bend it a little bit or if you stretch it a bit, it will go back into its initial position. And these two are, of course, especially pronounced if it's above the glass transition temperature. So the crystalline regions, they are very strongly packed or closer packed. And they have a very high affinity to other chains. Or we could also say high adhesion between the chains, because this is what causes the crystallization. And these things, of course, leads to an increase in hardness. Because the material is joined together much more strongly, but it also makes it brittle, because once it breaks, you break along a crystalline area and then it fails catastrophically. So this is very typical of a crystalline material. And another consequence of this high adhesion between chains is that it's more difficult to dissolve. Dissolves more. Maybe better, more difficult to dissolve. Okay, so this is kind of a summary of the individual parts. Now we take them together and let's see what comes out in this composite. But firstly, if we merge them together, what we get is an increase in toughness, and we will get to this a bit more in a second. But you see that we have hardness coming from the crystalline parts, so that gives mechanical stability, but we also increase elastic properties and ductility from the amorphous parts to dissipate energy, and this makes the material tough. Then we have higher operation temperatures compared to an amorphous, so high operation temperatures, because we can go above the glass transition temperature. So where a normal amorphous polymer fails, we can still use a semi-crystalline polymer. Very often, as a consequence of the chain architecture that we need to provide to actually get this high adhesion between chains, we also have a high Young's modulus. Not always, but typically. Simply because the chains stick well to each other. And now, because it's difficult to dissolve these semi-crystalline parts, no, it's more difficult to dissolve because the chains are closer packed, so it's more difficult for solvent molecules to enter, and they need to overcome the lattice energy of the crystal in order to dissolve. That makes it more difficult. So that means that they're more resistant towards chemicals. And this is why very often you store solvents in semi-crystalline materials, in semi-crystalline polymers. Okay, this is for the plus side of semi-crystalline materials. But there's also disadvantages. And one disadvantage is you cannot make elastomers from it. No, that's simply a property that is related to amorphous polymers because we require this high chain mobility. Which is something we can easily live with because normally you design a polymer for a certain function, so one doesn't need to have it all. One other thing that may be a bit more severe is that it cannot be transparent. And this is something I want to go in a little bit more detail. So this is really a key disadvantage, or also a way to spot semi-crystalline polymers is to look at the optical properties. And semi-crystalline polymers cannot be transparent. Why is that? Maybe we can just put this here. An amorphous polymer consists of a single phase. So if you look into your material, it just has polymer chains, and the refractive index is equal everywhere. An equal refractive index. If we look at the semi-crystalline polymer, then we have amorphous regions that are less densely packed, so they have a certain refractive index of the amorphous parts, but they also have regions where they are much tighter packed, and the refractive index is, in a sense, a molecular consequence of the density or the electron density of a material. So in these closer packed regions, we have a second refractive index from the crystalline regions. And we've also seen that the whole material essentially looks like an amorphous matrix with small semi-crystalline inclusions. So refractive index 1 or N1 from the amorphous regions and refractive index 2 from the semi-crystalline regions. So now, whenever you have a material that consists of two phases, two very small phases, with different refractive indices, you get light scattering. Let me just note transparency. Two different refractive indices. And that means we have light scattering. So in a sense, a semi-crystalline polymer is exactly analogous to milk. In milk, we have water with a certain refractive index of water as the continuous phase. And in this milk, there are small oil droplets with the refractive index of oil, which is higher, that are dispersed in this aqueous phase. And the oil droplets scatter the light. So if you have ambient light, which is composed of all different wavelengths, you create a white impression because the white light scatters in all directions. Now in a semiconducting polymer it's exactly the same. You have an amorphous matrix surrounding or forming the matrix and very small semicrystalline inclusions that are within this amorphous matrix. They have a different refractive index and this creates light scattering. And that means that a semi-crystalline polymer will always have opaque optical properties. Light cannot easily penetrate because of scattering. So the light is scattered at semi-crystalline domains. And just as a word of warning, that's something that people typically confuse. That doesn't mean that the light is reflected at the individual crystal planes of the crystalline part. The visible light is way too large to actually do this. For this you need X-rays. But light scattering occurs at the entire, if you want, blob of semicrystalline material. So the entire lamella. This is what causes the scattering. Nevertheless, scattering means you redirect light in space, and that means if you want to look through, you cannot because it looks opaque, because the light goes in all different directions. Okay, so this is really a disadvantage of semicrystalline materials. And now I just want to briefly show you, maybe we can go back here. Briefly show you the mechanical properties. So this is what we just put on the blackboard. So we can have hard materials which require a high stress to break. But we can also have tough materials that require a lot of energy before breaking. And the energy here is the area under the curve in this stress-strain diagram. And now let me just show you briefly how this looks like for a semi-crystalline polymer. So this will answer why these polymers are so tough. So in the stress-strain diagram, we can either have amorphous polymers that you can strain a little bit and then they break. In this case, below Tg. Or if the amorphous polymer is above Tg, it's an elastomer, then you can strain it for a long time and you hardly require any stress. So this is an elastomer. And then you can have a semi-crystalline material, which depending on the material can be more or less sloped. But let me just draw it underneath. That looks like an amorphous polymer, but then suddenly you get an inclusion here and it starts to deform more and more and eventually it breaks. And just for completeness, we can also have a fiber that is very stiff. No, you cannot strain it a lot, but it requires a lot of energy to actually do this. So something very hard in one direction. And now the question is, what happens in this semi-crystalline material here? Why does it deform so weirdly? I mean, the first thing that we can appreciate is that in the beginning, the slope looks very similar, so we can attribute this to the amorphous parts. Okay, and then the thing that is new is this entire part here that doesn't occur in the amorphous materials. So if we look at the molecular picture, what happens? In the first step, we have our amorphous material, some semi-crystalline domains, and then we start to orient, so we stretch the amorphous parts. A little bit similar to the amorphous part, and as we do this, we also orient the crystalline parts. And then, when the amorphous material breaks, what we start to do here is to increasingly pull away at these individual polymer crystals. So now these domains are aligned, and as I pull, I need to break the crystalline regions along their axes. So I start to pull here and get something like this, and it will look like this. So we need to pull apart the crystallites. And now you can imagine that since the crystallite actually saves quite some energy in these crystal domains, that's why they actually form, it requires a lot of work to pull them apart. And this dissipates a lot of energy, and that is why the semi-crystalline properties are so tough, can absorb so much energy before they finally break. And let me just show this to you maybe in some more detail here on the blackboard. So this is what you just seen on the blackboard. This is how it looks like schematically. So you start to get this small intersection that grows bigger and bigger, and this is where really the material flows and where you tear apart the crystallites. And if you look at this, you see that as you increase, you first stretch the amorphous parts, then you align the polymer crystallites, then you start to tear them apart, and eventually it breaks or it fails. Okay, so this is kind of the main reason why semi-crystalline polymers are typically high-performance polymers and used in applications where you need to have tough materials, hard materials, or material that generally withstand a lot of mechanical stress. And here you see how they can actually do this. Okay, with this, I'm at the end of this set of lectures about polymer materials, and I just want to take a few minutes to recapitulate these different substance classes. So amorphous polymers, if you've seen, are characterized by the class transition temperature. We discussed that this is the second order phase transition where the dynamics of the material changes, but not the physical configuration of molecules. We've seen that amorphous materials can be transparent simply because they are homogeneous material, and they can be ductile. And the critical factor is the entanglement molecular weight, so you need to have large polymer chains to actually get these mechanical properties of an amorphous material. They also move by a process called reptation, where they simply need to kind of snake around individual obstacles, which is not something that we have covered in the lecture, just kind of as a side note. Elastomers or elastomeric properties are unique for polymers. They need to consist of amorphous materials because we need to have this random coil structure. We need cross-linking and a mild cross-linking density at this, so that we have polymer chains that are fixed together, but still have large random coils in between, because this is what we actually stretch. And they need to be above the class transition temperature so that they can actually move lightly. And then we've seen that the elasticity is caused by entropy. Keep that in mind as a concept of entropic spring. And we've seen that they have some kind of weird properties as, for example, heating up when stretching, or a negative thermal expansion coefficient that we can very easily rationalize by these thermodynamic considerations, taking into account that entropy causes this rubbery or this elastic behavior. And then we discussed semi-crystalline polymers. So we saw that we need to now counterbalance the tendency of polymers to form a random coil structure, which is driven by entropy. And how we do counteract this is that we need to overcompensate the entropy by enthalpy. And this works either via van der Waals forces, where we then need to ensure that the polymer can order, and we do this by either using polyethylene, which doesn't have any side groups, or by controlling the tacticity of the polymer, so the orientation of the side groups with respect to the polymer backbone. And they can be atactic, which is random, this cannot crystallize, isotactic, which all side groups show in the different directions, which then can crystallize, or syndiotactic polymers, where the side groups alternate between the positions. Then we've seen that we can use hydrogen bonding, which is probably the most typical way of achieving something like this, and that's kind of the key trademark of nylon or polyamides. But we can also use more exotic interactions such as pi stacking to create a polymer crystal, which is very important in organic semiconducting materials. We've seen that they crystallize in lamellar structures and can potentially form spherulites. And then we've seen that a lot of properties change for semi-crystalline materials simply because they combine both properties of amorphous polymers and crystalline materials. For example, the mechanical properties are strongly enhanced. So we've discussed that they're much tougher because we now need to dissipate energy by destroying all these polymer crystallites. But we've also seen that they're more chemically resistant because it's much more difficult to dissolve a crystal compared to an amorphous material. But we've seen that the problem is that they cannot be transparent simply because they consist of two materials. So we can picture this similar to milk as semi or crystalline domains that are dispersed in a continuous amorphous matrix. And since these two materials have a different density, they also have a different refractive index, and this causes light scattering, so makes the material turbid or opaque. And we've seen an extreme case are polymer fibers where everything is aligned, and that makes it somewhat special and useful when you need anisotropic mechanical properties. Okay, with this, I'm at the end of today's lectures. Thank you very much for listening. Have a good day and see you soon. Thank you.